Hello, good morning. Once again, this is Mr. Steele. I'm here remotely. It's actually Saturday right now. I've got about an hour before I get to go see Fiddler on the Roof, performed by Franklin Theater Company. For right now, though, I do want to continue trying to make sure that these lessons are ready for you today, which in your time is Friday, March 23rd. And today we're going to continue what we started yesterday, where we started talking about the graphs of conic sections, and in particular about today the second conic section, the ellipse. So our essential question for today is, first of all, what are ellipses? What are their parts? So what are the different pieces of an ellipse? And how do their graphs and equations relate with each other? So we're going to do the same kinds of connections as before. We're going to first use an equation to write out or to graph the shape of an ellipse. So we can graph it just like this one right here. And then second, we're going to go backwards and look at the graph of an ellipse and see if we can determine all the pieces we need so that we can actually write its equation in a graphing form. Now first, before we start though, something you might have kind of in the back of your head that would be kind of tough is, well, you might not know what an ellipse is. What do I mean when I say an ellipse? In fact, some of you might think when I say ellipse, you might see this, a twilight sequel. Unfortunately, that is not an ellipse, that is an eclipse. Notice the word eclipse, it has a C in it. The word ellipse does not have a C in it. That's not the same thing. You might also think of an eclipse like when the sun and the moon like interact with each other or like block each other out, and so it makes that cool shape in the sky that makes it look like the hole in the movie The Ring. That's not an ellipse either. An ellipse is actually the shape that I'm making around the word eclipse. It's like an oval, or as I'll describe it a lot of times, it's like a circle with two different radii. So in fact, to get those things out of your head, we're not talking about Stephanie Meyer, who's probably busy right now swimming in her pool of money. Instead, we're talking about ellipses, the second conic section. So let's start with the definition. So what is an ellipse? I like to think of it as just a circle with two different radii, but in fact, an ellipse has kind of its own kind of a way of thinking about it. It's like all the points that are a certain distance away from 2 points. So it's all points, a set distance, from 2 points. So this time there are actually 2 points that function. I mean, there will still be a center, but there are 2 points. Those 2 points are called foci, or foci, it depends on who you ask. And then normally I would do this kind of cool demo where I take 2 push pins, I stick them in the wall, and then I take a piece of string and I show you how you can draw an ellipse that way. But in fact, it's hard to do that when you're not physically in the room. So instead, since I'm coming to you across the confines of time and space, I'm just going to leave that for later, or maybe you can look it up on YouTube, or maybe I'll look it up on YouTube before the end of this thing. But again, an ellipse is a little bit different. Instead of being all the points that are a set distance away from a single point, now there's 2 points actually that function towards making that ellipse. And so, of course, what is an ellipse? Well, we're looking at one right here. So if we were to draw those 2 points would be somewhere around here and here. So we don't have them. It's kind of hard to visualize without it, so let's just set that aside. Instead, let's talk about some other things. So first, another important component of an ellipse so I don't like that A. Another important component of the ellipse that wasn't a part of our discussion of circles yesterday is the major axis. So what is the major axis? It's the axis that is longer. Okay, so yeah, you might be criticizing me for the word, using the word axis in the definition of major axis. It's basically the line on which it's longer on the ellipse. So your major axis will either be one of 2 things. I used to call it X or Y, but instead it's better to call it either horizontal or vertical. So those are your 2 options for a major axis. So let's finish this. Vertical. So one or the other. So if we look at the ellipse at our left, we can actually tell which one's the major axis. Looking at it, notice that from the center it's 2 up and 2 down, but 4 left and 4 right. That means the major axis is going to be the longer one. So the major axis is right here. And the major axis would be described as horizontal because it's longer side to side. It's not taller. So we would say and answer for this particular ellipse that the major axis is horizontal, or you could even call it X, but I prefer to see horizontal. Well, if we're talking about major axis, you could probably figure out that there is something called a minor axis. Now I'm not going to define it and write out the axis that is shorter. That'd be kind of silly. I think instead you can just kind of see that the minor axis would then be the other guy. So in this case, our minor axis would be vertical. It'd be up and down. So it's just something to keep in mind. You won't be asked to analyze and say what the minor axis is, just be able to know where it is so that you can find some other pieces. So there we go. There are our first real definition that we had to look at, the major axis. It's the longer part of the ellipse. And then the reason that we look at the major axis is because it lets us find and describe two very important points. In particular, those are called the vertices. So now what are vertices? Well, they're the points of the ellipse on the major axis. So it's actually a very simple definition, and it just means that you have to look for the two edge points of the ellipse that are actually on the longer part. So since it's longer horizontally, side to side, our two vertices would be right here in that first red dot, and right here with this second red dot. So those are actually the vertices. So I'll just label them with a little V for now. But notice that they're on the major axis. The horizontal axis, those two furthest out points, are the vertices. Well, now, if we have vertices, obviously those are 2 points that we're going to plot. We also have what are called covertices. So, and I'm not going to bet you that you can't figure out what the definition of covertices is, because it's probably going to be pretty obvious. These are going to be the points that are on the minor axis. So these will be the other 2 points that we'll actually plot when we first start. And you'll see how we plot that in the next example. But basically the covertices will be these other points. So notice we hit the two far out ones over here. Well, vertically then on our minor axis we'll have this one as a covertice and this one as a covertice, or a covertex, I don't actually know for sure. So those are CVs. And so there we go. We have 4 points basically in addition to the center, but the center is not actually on the ellipse. So the covertices and the vertices end up defining basically the edges of our ellipse. We would just fill in everything from there. And now you might say, looking at your homework sheet or your note sheet in front of you, that hey, there's all these other things. There's eccentricity and there's foci, and well, yeah, there's that other stuff. But in fact, we don't have to worry about that just yet. We'll come back to that at the end of this lesson so that we can make sure we hit everything. Instead, what I'll point out is that the other two things we'd want to talk about, just like we did before, would be domain and range, like same stuff as yesterday. So we can still find domain. So domain is still all the x values. I'm not going to make you write it down again. Instead, what I'll say is that we can look at this ellipse as a refresher and point out what the domain is. So looking at it, domain, remember, talks about the x direction. So for here, since our x is longer, we start at that vertice. And notice that if we squish this ellipse down all the way to the axis, to the major axis, we'd have those points. Notice the smallest one is -4 and the biggest one is 4. That means that our domain would be -4 to 4. So domain, same thing as yesterday. It's all the x values or inputs that work for our function. Second, we'd also have the range. So range is also a thing that we'll look at for the ellipse. It's really why we study conic sections as kind of a conduit to getting in domain and range. For the range, we're looking at y values. If we start the same way, we start at this covertice down here. It just happens to be a covertice because the minor axis is here. Looking at the smallest one we hit is -2, and then we go all the way up to this one at +2. So if we're going from -2 to +2, that means our range is -2 to 2. So in other words, what I'm trying to say is this is exactly the same as yesterday. Domain and range are exactly the same. We can look at the stuff on here. In fact, it'll be easier than circles because we won't ever have any that, or at least we won't give you any for right now that have weird numbers. So there we go, all the things we need. We know what an ellipse is. It's just a kind of a squished circle, like or a circle with 2 radii. And those 2 radii I'm talking about are like the 2 and the 4. It has a major axis, which is the longer side, either horizontal or vertical. Also has a minor one that we don't care about as much. The vertices are the points on the major axis, and the covertices are the points on the minor axis. And we can still analyze domain and range. Everything else we'll worry about later. So next, let's take a look at an actual example where we'll take the equation, we'll dissect what each piece means, then we'll go and we'll actually graph and analyze an ellipse. Okay, so here is our first example. First ellipse we are going to graph. And again, this will be kind of where we transition. You'll no longer be doing something you've already did in geometry. So the first ellipse is going to be x squared over 25 plus y squared over 9 equals 1. And so the first thing I'll look at is the center. And what I'll tell you about the center is that it's not that point that's hanging over here. It's going to be whatever point makes the individual pieces, the x squared one and the y squared, equal to 0. So we have to ask ourselves what makes each one equal to 0, just like we did yesterday. Well, when you look at it, x squared and y squared by themselves tells us that each one is going to have a center component of 0. So our center is going to be at the origin, just like it was yesterday. So I'll plot it right down and make it a nice big one so that I cover up my poor graphing. And so there we go, we have the center. Next thing I want to look at, though, is the major axis, because we talked about what it was. It's the longer side or the longer piece of the ellipse, either sideways or up and down. But the question is, how do we find it? The way we're going to find the major axis, so I'll write this down since it's important enough to know, is it's going to be found by looking at which denominator is bigger. So here's what I mean. Well, bigger denominator is pretty descriptive, right? I mean, it's not that hard. So what we have here is that the bigger denominator, not bigger denominator, is going to be this one. So our bigger piece comes from x squared over 25. Well, x is the horizontal axis, so that means our major axis is going to be horizontal, just like x. And again, as I said earlier, sometimes I used to call that even x, like the major axis was x. That just means it's going to look more like this. It's going to be a longer ellipse as opposed to a taller one. Like, that's not what we're going to have. We're going to have a horizontal major axis. So there we go. We can find that just by looking at the denominators. They tell us which one's which. That won't be the case all the time going forward, just for now. So what's next? Well, the vertices. So as we said earlier, up in the first one, the vertices are the points on the major axis. So we have to figure out, by looking at the equation and what we have here, where those points are going to be on the major axis, like side to side. Well, the way we look for the vertices is we look at our denominator. So in this piece, like for the vertices, since x is major, we look at the first term, the x squared term, and notice that on the denominator is 25. Well, to figure out how far we're going to count, we're going to take the square root of 25. The square root of 25 is 5, meaning that we're going to count 5 over and 5 back from that center. So 1, 2, 3, 4, 5. Our first of the vertices is right here. 1, 2, 3, 4, 5. Our second of our vertices is going to be right here. And then, of course, how do we write it down? Well, we just mark the coordinates. Notice in this case we've got 5, 0, and on the other side we've got negative 5, 0. So you could write plus or minus 5, 0, but since it won't always be the same number, I'm just going to write them this way. So negative 5, 0 and 5, 0 are our vertices. The way we found them is that we counted out square root of 25 along the major axis. And again, that should make sense because we were under there. For the covertices, I need to know what color I used before. Covertices looks like to use baby blue. So for the covertices, we're going to do the same kind of thing. So what we'll do is we'll look at the minor axis, the other term, in this case, which is y squared, and we'll check its denominator. Those ones have a denominator of 9, or that piece has a denominator of 9, so we're going to count out square root of 9 in the minor axis direction. So in this case, we go to the center. Our minor axis is vertical, so we go up square root of 9, and square root of 9 is 3. And we go down square root of 9, which is also 3. So the covertices again have coordinates. The first one will be 0, negative 3. And the second one will be 0, positive 3. And so we have we have 4 points now on our ellipse. We've got the 2 on the major axis, the vertices, and then in baby blue, the 2 on the minor axis, called the covertices. Well, the next thing we should do is actually graph out what the ellipse is. So I'm going to actually do my best to graph it. Sometimes it's easier. Nope, I'm not doing any better than I did yesterday. Okay, that's pretty good. Maybe if I can get half, I'll just copy it like that. Look at this. Watch me cheat. There's half of my ellipse. Let's see, my question is, can I actually copy and paste it? Will it let me do that? Actions, tools. Nope, it won't let me do it, so that was a failure. So, fail there. Let's see. Instead, I've got to draw the bottom of the ellipse. All that to eventually have to draw the dang thing. There we go. And so there is my ellipse. I've drawn it. It's an oval. There we go. Definitely not a circle. So now what else do we have? Well, to finish it off for now, I said we're going to ignore these two guys. We'll deal with the foci and the eccentricity at the very end. Instead, what we want to do is we want to look at the domain and the range. So thinking about it, this should be pretty easy. It's just like a circle. Start on this side. The smallest point we have is at negative 5. And then we have graph all the way across. This is really cop-out shading, but whatever. Have graph all the way across up until 5. So clearly our domain is going to be all x values. So x is a member of hard bracket negative 5 to 5. As far as our range, well, you can probably see it just as quickly as I can. The smallest value we have for y is negative 3. It's down here. Then we go all the way up until we hit positive 3. And so our range will be y is a member of, because we're looking at y values, negative 3 to 3. And there we go. We've analyzed all the basic stuff and all the basic components of an ellipse with without having much trouble. The center came from the same place it did for circles. The major axis comes from looking at the denominators of the two terms and figuring out which one has the bigger one. That becomes our major axis. To find the vertices, we count out the points. I'm going the square root of that denominator in the major axis direction. To find the covertices, we take the square root of the smaller denominator and count out that far from the center in the minor axis direction. Domain and range, same thing as before. And so there is our first ellipse. Okay, so we're here to look at I've realized just now that I start most of these videos with the word okay. So let's try this without it. So, blah, 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 blah. Well, here we go. Let's take a look at a second example here, another ellipse. This time we're going to look at the one represented by the equation x minus 2 squared over 16 plus y plus 3 squared over 36, all equal to 1. So once again, what you might start to see is that, well, this equation looks a lot like the last one. That's because this is called graphing form. So it's something that we like and that we use so that we can very quickly find all the components that we need to graph out an ellipse. So just like the last one, I'll start with the center. So taking a look here, we'll look at these two terms. What makes each of those tops, the squared parts, equal to 0? Clearly that's going to be 2 and negative 3. Oh, I don't know what happened there. 2 and negative 3. So my center is going to be at the point 2, comma, negative 3. There's my little dot, and I'm ready to go. Second, my major axis. Well, remember the last time, the way we found that major axis was by looking at the denominator and seeing which one is bigger. So looking at this one, what you might see is that we have a different case than the last time. In this particular equation, the bigger denominator is right here, 36. Since 36 is bigger, that means the y term has the bigger denominator, which means that we're going to have a vertical major axis. Again, you could probably abbreviate vertical if the line's really small, but I like vertical. What that means is that our ellipse is going to look more like this than like this. It's going to be a taller ellipse than a longer ellipse. Okay, so now how does that change what we have? Well, because of that, because this is a vertical one, its major axis is vertical, that means the vertices, we're going to look at the y term. We're going to start with that 36. We're going to go square root of 36 from the center, up and down. So in particular, we'll start at the center, down 1, 2, 3, 4, 5, 6. So there's one of our first vertices. There's the first of our vertices, and then 1, 2, 3, 4, 5, 6. The second of our vertices is right there. And our coordinates are, let's see. This time we're at x equals 2, so it'll be 2, comma, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9. So 2, comma, negative 9, comma, 2, then up 1, 2, 3. 2, comma, 3. So there are our vertices. So how is that different? Well, before, because the x was our bigger denominator in the first example, that meant that our vertices were side to side, the 2 points on the edge left and right. Since our major axis now is vertical, though, we look in the y direction, and so our vertices are the high and low points. Next, the co-vertices. So trying to remember what color I used last time, I don't remember. I used light blue. So for the co-vertices, well, you can probably predict what I'm going to do. The same kind of thing as this last one. So our smaller denominator is right here, 16. So for the co-vertices, we're going to count out square root of 16. So go to my center. Square root of 16 is 4, so I'm going to go 4 to the left. There's one co-vertice, and then 4 to the right, which gives me my second co-vertice. Just like the last time, we can just figure out what those coordinates are. The first one is negative 2, comma 3. So I'm literally using the look at stuff method. So I'm looking at the points and figuring out what their coordinates are. The second one is 1, 2, 3, 4, 5, 6. And that's going to be 6, comma, negative 3. And so there we go. We've got our vertices and our co-vertices. Now something you might ask yourself as you look at this would be, well, where could I see those co-vertices and vertices without actually looking at the graph? And what I might tell you is you might notice that there's some similarities here. Notice for the vertices, there's a 2 for the x-coordinate in both times, just like there was for the center. And for the co-vertices, there's a negative 3 as the y-coordinate for both of them, just like there was for the center. Well, that shouldn't be a coincidence because they're always along those lines. Like the major and minor axes go through the center points. And so notice they're both the vertices are along the major axis, the co-vertices are along the minor. Well, next, before I finish domain and range, I might as well draw in my ellipse. So I'll do my best to draw it without embarrassing myself. So far, so good. Haven't completely destroyed it yet. There we go. There is my second ellipse. It's a little lopsided down here, whatever, it's okay. Looks more like a potato. Nobody's worried, nobody's watching. Oh crap, you guys are watching. Oh well. And so there we go. We've got vertices, covertices, drawn the ellipse. Now I just want the domain and range. Well, now of course we can find the domain and range just by looking or using the look at stuff method. But in fact, you might also notice that the vertices and covertices actually give us a lot of great information. So starting with the domain, the smallest x value is -2, and then we go all the way over here to the biggest one, which is 2, 3, 4, 5, 6. So our domain is x is a member of, hard bracket, -2, comma, 6, hard bracket. Now what you might notice is that -2 and 6, they showed up before right here. -2 and 6. Those are the x-coordinates of the covertices in this case. Well, for the range, you'll see that there's some similarity with the vertices, again, depending on the major axis. The smallest one is -3, -4, 5, 9. The smallest one is -9. So again, what's that coming from? It's coming from the y-coordinate down here. The biggest one is +3. So my range is y is a member of, -3 to 3, all hard brackets. And again, -9 and 3, notice they were the y-coordinates of the vertices. So there's a couple different ways we can do it. I prefer using the look at stuff method for these guys because we can just look at stuff, and looking at stuff is fun. But of course we can also see that there's some connection between the vertices and the covertices, since those represent those extreme outside points on our graph. And so there we go. There's a second ellipse that we have now graphed. Yay. Almost said okay. Almost said it, but I didn't this time. So what you can see here in our third example, which we've just moved on to, is that the equation doesn't quite look the same. Like, notice that our first and second examples up here, number 1 and number 2, both had denominators staring at us. Like, it was really easy to see. They were both equal to 1 also. Notice over 25 over 9 equal 1, over 16 over 36 equals 1. Well, in this example, notice that our denominators aren't there. It has x minus 2 squared plus, there's a coefficient of 4 in front of it, y plus 1 squared, and it's all equal to 16. Well, since this isn't in graphing form, basically it just tells us we're going to have to do a tiny little bit of algebra so that we can get it in graphing form, so that we can then go through and do everything like we would normally. So what I mean is this. Like, take our equation. In fact, I'm going to cheat. I'm going to drag it from right here, copy it, paste it, there it is. And what I'm going to do is I'm going to go ahead and make this thing in graphing form. And the way I'm going to do that is I'm going to divide by this number. I want it to be equal to 1, so in order to do that I've got to divide both sides by 16. If I divide both sides by 16, that means I'm going to divide each of these individual terms by 16. Now what does that do? Well, on the right side, you can clearly see 16 by 16 is 1. On this first term, the x one, notice that it very clearly shows x minus 2 squared over 16, that's all perfect too. So it's like 2/3 of the equation are right and ready to go. Notice on this guy, 4 over 16. Well, 4 over 16 simplifies. This becomes a 1, which we don't even have to write, over 4, because 4 over 16 is just 1/4. That means the second term can be written as y plus 1 squared over 4. And oh, there it is. Like, notice that's the equation we want. That has graphing form. We've got denominators. We've got it equal to 1. Like, all the boxes are checked. We got what we need. So in fact, now we don't really need that guy. We can just look at this guy instead. This one should make you happy, or at least relatively happy compared to how that one did. So now that we've got our equation, we can go ahead and graph it. So I'll do it fairly quickly. Like, I center, that's going to be +2, comma -1. My major axis, well, it depends on the denominator. My bigger denominator is with the x, and x is horizontal. So I'll use horizontal. That doesn't fit. I'm going to just go with horiz. Okay, so first let's plot the center. So 2, -1. That's right about here. No, that's not right about there. It's right there. Now I need my vertices and covertices. Well, the vertices come from the major axis. Major axis is the x direction, so I need to think in terms of square root of 16 and then count that out in both directions. So -4 plus 4. They're my vertices. Their coordinates are -2, comma -1. And let's see, what is that? 2, 3, 4, 5, 6, comma -1. And so I've got my two vertices. In fact, I haven't been doing this lately, but I could mark them with a little v. tell me that they're vertices. Okay, next my covertices. Well, the smaller one is 4. So for the covertices, I'm going to go up square root of 4, which is 2, in the y direction, since y would be the minor axis. Up 2, down 2. I've got my two CVs. They're right there, CV and CV. And now I just need to mark their coordinates. Well, one is 2, negative 3. The other is 2, 1. Again, depending on which one's which, it just depends on, like finding them just depends on which one's bigger. Since the bigger axis is this way, those are the vertices. On the last example, the bigger ones were up and down, so is the tall ones. Next, I can draw in the rest of my ellipse. So let's see how quickly I can do this. Actually got to go get ready to go to the play in just a second. So there's my ellipse. I'll save my thing just so I feel good, know that it hasn't been erased. And last, I'll find the domain and range, since those are pretty quick to find here. So domain and range. So what are they? Well, obviously we're still going to be enclosed. For domain, my first one, my smallest x value is negative 2, and it goes all the way over here to positive 6. So my domain is negative 2 to 6. And for the range, my smallest y value is down here at negative 3. So it's going to go from negative 3 all the way up to the biggest y value, which is 1. Good old Uno. And there are my domain and range. So I have now graphed a third ellipse. This one wasn't in graphing form, but the way I fixed that was just dividing everything by whatever that number was on the right side to get it equal to 1, and then I did everything just like I had before. So good job me. So what can we do from now on? Now we can actually try going backwards. Like, I don't think you really need to try it for the sake of time, so let's try going backwards this time. Well, so we're back. We're going to now look at how to go from a graph of an ellipse into the equation and eventually find that. Now what you might notice on the right side, and just like on your handout, is there's not as much information here. I'm not going to ask for the eccentricity and foci when we do something like this and go backwards, but at the same time it's still good. So what we want to do here is we want to take the graph and we want to use what we know about ellipses to take the information from the graph, distill it, and get the equation. So that's our goal on this one. So looking at it for a second, what we can kind of start with is the most obvious stuff. Like first, that would be the center. Like what is the center? Well, we just look and figure out where is the center. It's at negative 2, negative 3, negative 4, negative 5. Looks like my center is at negative 5, 0. Now the way the center helps us is it lets us put in the first two pieces. So basically I'll try to use color and stuff down here to kind of mention it, or to get everything in here. So for the center, we look and we go, okay, those two things, negative 5 and 0, have to make the x and y terms equal to 0, the squared parts. So for the first one, if negative 5 is going to make it equal 0, that would be x plus 5 squared, just like yesterday with the circles. And then for the other one, it's just going to be plain old y squared, because it would be y minus 0 squared. And the other thing we can add, just even without the center, is that it's always going to be equal to 1, like we know that. And so there's our first two things. So we've got the top parts. Now what we need to do is we need to figure out how to put in those denominators. Like how can we get those denominators in there? So let's switch to the second part. That's going to come from looking at the major axis. It's going to help us a little bit. So when I figure out the major axis, remember that's the one part that's longer, either vertically or horizontally. And if we look at this guy, it looks like it's longer vertically. Like this is a taller ellipse this way. There's 4 up and 4 down, 3 left, 3 right. That means that the major axis is going to be vertical in the y direction. What that tells us is that from there we should have the bigger number here. Like we should have that underneath the y term, underneath y squared. So again, it doesn't give us anything directly, but it does help us a little bit. Now, as far as the rest of the equation, in order to finish it and put it up here on this line, what we need to actually look at and count out how far away the vertices and the covertices are. Because basically what we want is we always know that we figure out that distance away and find the vertices by counting a certain distance away from the center. So for our vertices, since the major axis is vertical, we're looking right here. Notice if we go up 1, 2, 3, 4, we hit the point right there. Well, since this is 4, and since going down from the center is also 4, what that tells us is that we're going to have 4 equal the square root of whatever number goes here. So of course 4 is equal to the square root of 16. That means that in the y direction, we have to have 16 on the bottom. Or more specifically, I guess I should probably put it as 4 squared. So 4 squared is what's going to be underneath here. That means we're going to be over 16 in our equation at the end. For the covertices and everything, for the other part, let's see, I think I used baby blue. So for the other guy, we do the same thing going in the left and right. So we go looks like 3 this way, so that we get to our covertice right there. And 3 to, oops, terrible line. 3 to the right, we get a covertice right there. Since they're both 3, that means that this is going to be 3. So we're going to have to count out 3 in that case, which is the square root of 9. And we'll put 3 squared underneath it. So now what does that tell us? Well, we can actually write our equation now, right at this point. Like we're already there. We can just go ahead and say that the equation is x plus 5 squared over 3 squared, which is 9, plus y squared over 4 squared, which is 16, all equal to 1. So our equation is right there. And we've got our equation. So that's really all we have to do. We use the center to set up the top parts. To get the denominators, we just count. So those denominators come from counting out how far away the vertices and covertices are. And then we square them, put them in there, and it's all equal to 1 in graphing form. And that's all we have to do. It's actually pretty easy. Now, of course, with everything else here, we could actually, I don't have to do that, we could actually find all this other stuff. So like for the vertices, we could look and say, okay, what are those coordinates? Well, it looks like it's going to be -5, 4. And the other vertice, which I didn't dot, but would be which would be right down there, is -5, -4. So again, this is just extra information. We already did what we wanted to. It's kind of like, check, we already got it. Covertices, it looks like we'll have, that's -5, -6, -7, -8. We'll have -8, 0. And we'll have, right there, -2, 0. So we got both those guys. And then for domain and range, really quickly, the domain, it'll be the smallest x value to the biggest one. The smallest one's right over here at -8. The biggest one is at -2. So our domain is -8 to -2. Actually, you can kind of see that told, or kind of implied to us in the covertices. And then for the range, it'll be -4 all the way up to +4. Because again, the smallest value is -4, biggest one is +4. And so we have our range as well. And so we've been able to not only go backwards to write out what the equation was just by basically looking at the center and counting some stuff on the an ellipse, but we're also able to do all the analysis information just like normal. So let's do one more, just because. Let's make sure we get it right. I'm not going to change color or anything. Let's just go through it as quickly as we can here. So first, looking at this guy, we want the equation. So we'll start with the center. So my center is at -2, 4, it looks like. And this one's pretty clear. My major axis, this thing's a really long ellipse. So this would be a horizontal major axis. So I'm just going to go horiz. Excuse me. So what does that tell us? Well, first, we basically get the first part here. We'll have x plus 2 squared over something plus y minus 4 squared over something equals 1. So now as far as everything else, we just need to count. So first for the x's, since the horizontal major axis, this is going to be the big number. So again, I'll just mark that down once so we remember it. So the bigger number is going to be in the x direction. We go over 1, 2, 3, 4, 5, 6. Since we're going over 6, we've got to go 6 squared, and 6 squared is 36. For the y, the smaller one, clearly that's smaller, we go from the center up 1. So if the small number is 1, we square it, well, that's also 1. So we can write it that way, or we could put plus y minus 4 squared just sitting down there. Next, for everything else, we can just go ahead and actually find those points. So starting with the vertices. The first vertice versus the vertices would be right there. The second one would be right here. Looking at this one, it looks like we'll have -8, 4. So there's our first of the vertices. Our second one would be, looks like 4, 4. So again, I'm just writing down the coordinates. So what were the x-coordinates? We'll need those later. They were -8 and 4. And covertices, those are up and down. That's going to be this point and this point. This one looks like it's -2, 3. The other one looks like -2, 4, 5. And so there we have the covertices. Once again, all we're doing is we're checking. We knew which one is the major and minor axis by looking at which one is longer, so we're able to label those guys. And lastly, for my domain and range, very quick to do. I've looked at the smallest x value. I can actually see in the vertices exactly what I saw over here. Smallest one is -8, goes all the way up to +4. So -8 to 4. And for the range, it goes from +3 up to +5, just like we see in the covertices. And so once again, we've been able to go backwards from the graph of an ellipse to actually write out the equation and then complete all the analysis information. It really only takes the center and some counting in order to get the equation. Everything else is just the same meaning as before. So good deal. Now that we've looked at how we can use the equation of an ellipse to actually graph the shape and also go backwards and use the graph of an ellipse to write out the equation, the only thing left we really have to do today before I can release you to start the homework and then eventually take standard quiz is we have to look at those other two pieces of information that I didn't cover earlier. Specifically, I'm talking about the foci and the eccentricity. Like, neither one of these two guys did I actually hit on earlier in the lesson. I just kind of skipped over and said we'd do it later if there's time. Well, I think there's time because this video has actually gone a lot quicker than I thought, probably because I just taught this in year long not too long ago. But I do want to cover how we can find these things and what they are. So if you want to, you can add this in the vocabulary section, or you can just add it separate sheet of paper, somewhere else on your paper, wherever you can find it. Excuse me, we're going to go through the process for finding both these two things so that you can have complete analysis for each of your shapes. So first, what are the foci? Well, foci are, most simply, they're 2 points on the major axis. I mean, that's nice to know. So there are 2 points on the major axis. Now, what is significant about these 2 points? Because we already have the vertices, which are on 2 points on the major axis. Well, these 2 points are c units away from the center. So this is a little weird. You're going, okay, well, what does that all mean? The c units away from the center? Well, like, basically, these are the 2 points that we would use to actually draw an ellipse. Basically, that c number is how far away they are from the center. So what we'd see is, like, basically the foci for an ellipse would be, if we already graphed it, it would look like a point about like right here and right here. Or if it was a vertical one, vertical major axis, we'd have a point right here and a point right here. Like, they're those 2 points that if we had like a string to tie around those two big push pins, we could actually drag it around and draw the exact ellipse out. I wish I had a way to do it on the computer, but I don't. So the most important thing for you is that to recognize that when we talk about the foci, we're talking relative to the center. So we're going to be looking at the center itself, and that they're going to be c units away from the center. So we first, of course, have to know what in the heck c is. So c is a number that we can find by looking at the pieces of the equation. So specifically, c is going to be equal to the square root of the big denominator minus the small denominator. And this is only for ellipses. It'll be different when we get to a different shape, but for now it's just going to do this. It's going to be equal to square root of big minus small. And again, it'd be a lot easier to actually explain this to you if I could actually show you what I mean with a picture. Since I can't, we'll just have to go with this. So basically what we need in order to find the foci will be the actual center, the coordinates of the center, and then the c value. So like, basically my process, let's just write out the little plan here, like the plan to find it. In order to find the foci, which I'll do a couple times in just a second, is we start by calculating c. So we just, subtract the big number minus the small number, take the square root. Then second, after we've calculated c, we write down the center, because that's where it's going to be relative to. And what I mean is, specifically, I mean like this. Like, you'll see me do this a couple times, but I write down the center as like h, and then I leave a lot of room, and then I write it as k, and again leave a lot of room. The reason is we'll put it in there somewhere. And then third, the last thing we'll do is we'll plus or minus c. So we'll add and subtract at the same time. We'll only have to write it one time, plus or minus c, with the major axis coordinate. So basically this will be the way we guarantee that our foci are on the major axis. So again, this might look like it's a really complicated thing because I've written down 3 steps and it sounds kind of weird and you can't really envision what they are, but actually finding it's really, really easy. So let me get the color up here, and then I'll go to my first equation and start taking a look. So like right here. So first, the foci for this equation. So what I need to do is I of course need to find c. So calculating c in this first example, and this is for some reason not labeled. This is example 1. So example 1, foci. Well, to find c, as I said, it's the square root of big minus small. So square root of big minus small, it's going to be square root of 25 minus the small one, which is 9. So c equals the square root of 25 minus 9. Well, 25 minus 9 is 16. So c is actually equal to 4. It's a whole number. Like, that's kind of interesting. And so basically for our foci then, now that I've got c is equal to 4, I'm going to take it, I'm going to write down my center. My center is 0, comma 0. So notice that I've left some space in here. I've got 0 and a little bit of room, comma 0 and a little bit of room. Now what I want to do is I want to add plus or minus c in the major axis direction, because my two foci are going to be somewhere around like right here and right here. Like, those will be my foci, the 2 points that all these other points in the ellipse are the same distance away from, or the sum of the distances away from is the same. Well, if we think about it then, the major axis is horizontal, so those coordinates that are going to change are my x coordinates. So I'm going to really have, for my foci, 0 plus or minus my c value. Well, of course, 0 plus or minus my c value, that's just, well, 0 plus or minus 4, that's just plus or minus 4. We can actually simplify this one, and so my foci are going to be at plus or minus 4, comma 0. And those are exactly the coordinates that I plotted down, because I have foresight and I recognized as soon as I was writing this problem what it was going to come out to be. So again, find c, square root of big minus small, add it to the major axis component, and then simplify if you can. Oftentimes you won't be able to simplify, so that's all you can do. So we've got one foci, or one set of foci for the first equation. Let's look at example 2 and do the same thing. So again, remember, it's kind of a couple steps. So we basically find c, simplify that as best we can, then we go on and we write down the center, we figure out which one's the major axis component, and then we add plus or minus c to that place. So again, it doesn't actually have to be hard. Like, it's just one of those things where you just have to kind of know where you're going with it and have a plan. You'll be fine. So first, for this one, you need to find c. c is going to be square root of big minus small. So square root of 36 minus 16. That's going to be the square root of 20. And now the square root of 20 doesn't simplify to 4, but it becomes the square root of 2 times 2 times 5, which is equal to 2 root 5. So this time c is not going to simplify really nicely inside our foci. So we just have to kind of expect that. Next, just like before, I'm going to take my center, which is 2, comma, negative 3. Oops, 2, comma, negative 3. And then I space it all out so that I've got some room. I mean, that may be kind of extreme for spacing it out, although it would be just fine. So it's 2, comma, negative 3. I'll leave it that way in case I need to simplify it. And then I look and go, okay, my major axis is vertical, meaning that my foci are going to be something like this. Like right here and right here. So what's changing is my y component. Like, my y coordinate's going to change. So I'm going to add plus or minus square root of 20 right there. And of course that looks kind of messy, but I'm really just adding plus or minus c on that side. In fact, it might be easier to just kind of show that, oh, I'm going plus or minus c here. Of course, then we can simplify this and make it look nice. It's going to be 2, comma, negative 3 plus or minus 2 root 5. And there are my foci for example 2. And again, if we were to simplify and write out about what c is, we'd find that those are about the right points that I just plotted. So, example 2, look once more, let's do example 3. So of course, example 3, we have it now in graphing form, like we moved it over when we did the problem, but we'll do the same stuff. So let's start with c. What is c? It's going to be the square root of big minus small. 16 minus 4 is 12, and once again, square root of 12 can be simplified a little bit, and I'll leave it to you to figure out how I do this as 2 square root of 3. So 2 root 3 is my c value. So as I look at my foci, where are they going to be? They'll be along the major axis, so something like that. So somewhere in that range, maybe not exactly there, but close. So clearly I'm going to be changing the x-coordinate because it has a horizontal major axis. So that means I can probably do this without even doing the intermediate step. I'm going to add it to the major axis component, which is x. So that'll be 2 plus or minus 2 square root of 3, and then comma, negative 1. And there are my foci once again. Nothing really hard to find. In fact, if we wanted to, we could actually go down and do them for these guys, but for the sake of time, I'm not going to do that. Instead, we'll move on and we'll take a look at how you calculate the eccentricity, which is actually really easy compared to the foci. And so here we are, last little bit of information that we can find for an ellipse, and that's called the eccentricity. Now, if you've heard the word eccentric before, it usually means someone that's kind of kooky or weird. That's really not at all what this has to do with ellipses, so just get that out of your head, pretend you don't know it. Eccentricity is also not a place, even though the word city's in there. Instead, it's a measure of how round the circle or the ellipse is. So I'll describe it as a measure of roundness. So it's basically describing how circular or how much like a circle a given ellipse is. And so basically, the way we find it, or basically let's start here. Like, basically what it means is if the eccentricity is close to 0, what that tells us is that it's very circular. And that should make sense, because if you notice the value of 0, 0 is a very round number. So that means it would be very close to a circle. And in fact, if you looked at a circle itself and pretended it was an ellipse, you'd get an eccentricity of 0, because it's totally round. And if the value is close to 1, it's going to be not circular at all. And in fact, you get values close to 1 when you have a really long major or minor, or a really long major axis and a really short minor axis. So you get a shape that looks like this, or in fact this, which I think not coincidentally look like ones. Like notice you could just pretend they're a 1 or a sideways 1. And so in fact those are the two qualities. Now how do we find the eccentricity? Well, it's actually really easy because we've already found the c to get the foci. In particular, the eccentricity, which I sometimes call like a little e or an epsilon, or I guess sometimes they call it e, although I don't want to confuse it with 2.71828, so I'll just call it this. The eccentricity is just c, the value c that we found right here, like that same c, divided by the square root of the big number, and then simplified. Like that's the only other thing we have to do. So it's actually really, really fast to find. We just take that c value we already got, and then divide it by the square root of a big number, and we simplify it if any sort of thing happens. And that will give us a description or a number that describes how circular our given ellipse is. So let's test it out with the 3 examples that we already did. Okay, there we go. So example 1, so eccentricity. Well, we already have c. c is equal to 4, so that's nice. And then, of course, our big number, our square root of our big, that's going to be 4 over the square root of 25. And this is our eccentricity we're trying to find. Well, that's just going to be 4 over 5. So for eccentricity, we write down 4 over 5. And then, though, obviously 4 over 5 is a fraction. You can tell it's kind of a fraction that's close to 1. But if you want to, you don't have to, but if you want to, you can actually write it as a decimal and see that this is equal to 0.8. And 0.8 is pretty close to 1. So this isn't a super circular 1. And that should make sense, because 1 major axis has 5 units over, and the minor axis has 9. So it's not a super round one. Like if those numbers were really close, we'd have a really round ellipse. But again, all we do is take c, divide by the square root of the big number, and we get our eccentricity. So the second example, and notice this is going really fast because, well, it is pretty fast. It's a pretty easy thing to do. So the second one, for the eccentricity, take our c value. It's 2 square root of 5, and then we're going to divide by the square root of the big number. The big number is already circled in blue. It's 36. So the square root of 36 is 6. So 2 root 5 over 6. And of course we can simplify that to square root of 5 over 3. So our eccentricity is square root of 5 over 3. Now again, we want to see, like this one doesn't look particularly circular, but just to make sure, let's check the calculator. Let's see, square root of 5, so 5 square root divided by 3. It says the value is approximately 0.75. Let's see, so 0.75. So it's a little more circular than the last guy, although it might not look that way right now. Remember, my pictures are drawn really poorly. But again, it's not particularly circular ellipse. Very, very not circular. So again, c over the square root of big. Again, with 3, I could ask you to try it, but again, this goes pretty fast. So let's just go through here and actually do it. So for eccentricity, it's going to be 2 root 3 over the square root of the big number. The big number is 16, so the square root of 16 is 4. So we'll get 2 root 3 over 4, and that simplifies to square root of 3 over 2. So root 3 over 2, and I believe that is approximately 0.87. I can check again, but I'm pretty sure it is. And again, what you're seeing is this is definitely not a circle. Like no one's going to confuse this like football shape for a circle. Much more likely to be confused for Arnold from Hey Arnold than a circle. So again, nothing big. I'm trying to think if any of our examples here are like really, really circular. So let's look at this one really fast. Like I know it doesn't ask for the eccentricity, but I just want to kind of show you one where it's closer. So for eccentricity, we need c over the square root of the big. So this will be my last one I do here. And if you look up here, c, like which we didn't find because this was a backwards problem, would be 16 minus 9. That's going to be the square root of 7. And the square root of the big number, well, the square root of the big number would just be 4. So root big is root 16. So that means our eccentricity for this guy is square root of 7 over 4. We'll calculate that out just to check it out. Let's see, 7 square root divided by 4 gives me 0.66. Well, this one's pretty small too. It's almost not even still kind of the same thing. Like we're still not finding any that are really circular, so that's okay. That one, I guarantee you we have a really, really high eccentricity, so not even going to look at it. So basically what we did in the last little section here was we filled in the two holes that we had in our stuff. We found the foci, which are the 2 points from on the major axis that we could use to draw the ellipse. We find them with C, and then adding it to the major axis coordinate of the center. And then the eccentricity, which describes how round or how circular or circle-like it is. We found that by taking that C value again and dividing by the square root of big, the big number, the bigger denominator. Should probably throw that in there, so I will real quick. But again, neither one of these things is essential for graphing. Like we don't have to plot these in order to get an ellipse drawn down correctly, but they are helpful to properly analyzing it the way we want to. And so my phone is buzzing at me, so let me go check that and then I'll come right back. Well, with the eccentricity down and everything, I think that's pretty much it for today. That's pretty much all you needed from me. Might even have been better than me being here, just because I probably would have made a bunch of dumb jokes, made fun of Brant more, answered a bunch of Marcus's questions, distracted you a little bit. So instead, we pretty much covered everything we need for ellipses. First, we talked about all the pieces of an ellipse, like all the different little components that we had, all the things we could find from before. The new things were most of the major axis, the vertices and co-vertices, everything else we could do from before. Then we learned how to go from the equation to the graph of an ellipse, specifically by figuring out what the center was, just like yesterday, and then using the denominators to figure out how far to count out. That allowed us to find the vertices, which I usually did in red, and then the co-vertices, which are in baby blue. Did that a couple times, practiced it a little bit. Then we were able to go backwards by using the same kind of thing, just in reverse. We found the center to write the x, or the squared terms of the x and the y. We analyzed it a little bit to figure out how far to count out, and then we used that to generate the denominators, which were just by squaring how far we went left and right, and up and down respectively. After that, and doing all that a couple times, we then talked about the foci, which are 2 points that are very important and useful, not that we need them to graph, but instead we just talked about the process of it being square root of big minus small, and then adding it to the center, depending on which one is the major axis, as well as the eccentricity, which just tells us how round our ellipse is, and it really doesn't neither one is essential for graphing. It's not like you go up to an ellipse and you go, oh yes, there's my eccentricity right there. No, it doesn't work that way. All it does is kind of give us some measurements and some other further analysis information about the ellipse. So I hope that after doing this, since this lesson took me a couple hours to make, I hope that it has been very helpful to you, and that now you'll be able to kind of start on the homework, feel ready to go, and then on Monday when I'm back, I can answer any more questions. Also, if for some reason this video didn't get finished, or if you want to watch it again, you got confused by something, it's on YouTube. Like I'll upload it to YouTube in a little bit. So hopefully, again, you've had a great time. This has been useful. You haven't wasted a day while I'm in Southern California, at this time probably touring San Diego State. So anyway, this is Mr. Steele, signing off, wishing you a good weekend, a good standard quiz, and good ellipse homework completing and stuff. Have a good day.